Okay, so the first thing I'm going to do is talk a little bit about what parasitic turn-on is. We'll draw sort of an example circuit of where this might occur. I'll show you how the phenomenon manifests itself, why it actually occurs, and then we'll go through the math. If you want to skip the math, that's fine. There's a very quick sort of check that you can do, a sort of rule of thumb check to see whether this is likely to occur or not. But for those interested, let's crack on with it. So this manifests itself usually in applications such as H-bridge driving or half-bridge driver circuit. So for those unfamiliar, that's usually a MOSFET or some other sort of switching source. So it could be an IGBT, but in this case I'm going to use MOSFETs. So we have a high side MOSFET, we have some inductive load, which is, you know, like a motor or something like this, and then a low side FET. So this could also be something like a magnet, it doesn't have to be a motor, but anything that sort of is an inductive load, really, this kind of phenomenon occurs. So yeah, there's our two high side, low side drivers. This is connected to ground. This one will be connected to a positive power supply. Then generally you have a gate resistor here on both, and then usually some form of driving circuitry to drive the gates of the MOSFET high or low depending on some inputs. Now this is what the circuit looks like in the ideal world. In the unideal real world, what we have are some parasitic components. So I'll draw those now. The ones that I'm interested in are the parasitic capacitances that you have around a MOSFET. Namely, those are the gate drain capacitance, the gate source capacitance, and then the gate drain source capacitance, which I won't be looking at because it's not really important for this, but just so you know that it is there. Now, so this is the circuit. This is pretty much all we need. Now let's consider a situation where both MOSFETs are currently off. So we've got this connected to ground and this connected to ground as well. So the gates of the MOSFETs are held below. So not that this is important, but the high side driving circuit usually has some bootstrap capability. So you have some more small or some reference voltage there that this can be turned on and off below, obviously to switch the high side MOSFET on, but completely irrelevant for now, just thought I'd mention it. So let's say that we're going to turn on the high side MOSFET. So that guy, for all intents and purposes, is connected to the power supply positive voltage. This guy turns on, we get a current flow through here. This guy is currently off, current goes that way, and you know, that's how you drive some circuit like this, okay? I'm sure you guys are familiar with that. But something that at least I didn't know about for a little while, I only recently found out, is something called parasitic turn-on. And now that occurs where we've turned this on, and the drain of this MOSFET here, so if we were to look at the voltage at this point here, if I draw that with respect to time down there, so there's time and here's the voltage. At this point here, what happens is it's currently off and we switch the high side MOSFET on. This voltage here, with respect to ground, very quickly rises to essentially the supply voltage. And what happens here, we've got what's known as a very high dV/dt. That's a fancy way of saying the voltage increased very quickly with time. So if you were to calculate the gradient of that curve, that curve there, to do that you would take the change in voltage, which is the change in the y, divided by the change in the x, so dt, and that gives you your gradient. So often in power electronics people refer to things as very high dV/dt points and stuff like that. That's pretty much what they mean. It's just that the voltage is going to be increasing quite fast at that point. So why is that a problem? Okay, we've got a high dV/dt point there. What's the problem there? Well, I'm sure as well it's nothing new to you that the equation for current flowing through a capacitor is I equals the capacitance of the capacitor multiplied by the rate of change of the voltage. So there we go. We've got something there that's relating to the rate of change of voltage. So if this was a really big number, if the voltage changed super fast, what you're going to get is, you know, some proportionally large current flowing through the capacitor. Again, do we really care whether we've got some current flowing through this path here when there's a high dV/dt? Well, yes, we do. Because generally, like I said before, we have these what are called gate resistors. Now, gate resistors smooth off these transitions. So without a gate resistor, if we were to drive this point high, so we want to turn that switch on and then off, what we get is very sharp edges on here, which is generally not good because that's going to be causing, you know, this, again, because we've got these parasitic capacitances and the gate is essentially a capacitor, if you do a very sharp change, again, you're going to be pulsing a lot of current from your driver chip. It may not be able to source that current. So these can usually source up to sort of 1 to 2 amps pulse current. But you know, you could be pulling a lot more than that by doing this very fast. And it's also pretty bad for EMC reasons as well. So what we tend to do is add in a small gate resistance of maybe 10 ohms. And that just sort of curves off this, this edge here. Now there are some sort of funky things you can do with diodes and other types of resistors to change this turn off. So you can have a different turn on and turn off sort of slopes. But outside the scope of this video, all I want to explain now is that we have a gate resistor there, and that's why it's there. So now what we've got is a... Sorry about that, Amazon order. Anyway, where were we? So, yeah, now what we said, we've got some current that's related to the rate of change of voltage. Now that current flow is going to be through here down to ground. So, you know, Ohm's law, V equals IR. We've got a current here and a resistance there. It's going to produce a voltage drop across that resistor. If that resistor is too high, then, if the current's too large or the resistor's too large, either of those too high, then we're going to get a voltage proportionally high. If that voltage is high enough to turn the MOSFET on, then we get bad things occurring, which is where you've got this MOSFET on, that MOSFET on, and you've short-circuited your power supply, which is pretty bad because, one, again, you're going to be pulling a ton of current, essentially infinite current, depending on the, you know, you've got RDS on values of the MOSFETs, and you've also got the internal resistance of the power supply, but you're going to be drawing a large amount of current from your power supply. That's going to be putting a large amount of current through your FETs, and it'll be for a short period of time because these, you know, these little peaks that we're going to be observing don't happen for a long time. But if you're switching several thousand, you know, several 100,000 times a second, then eventually those are going to warm up, they're going to fail prematurely. And this is where this comes from. So now that we sort of understand the problem, let's take a look at the math. I'll redraw this circuit in a way that's a little bit more simple. So we're going to remove the FETs because they're not really needed for the analysis. We'll do some AC Thevenin equivalent analysis of that circuit, and we'll find out an equation that we can derive to basically so that we can plot this curve later on. Okay, so this is what the sort of simplified version of the circuit that we're going to be analysing looks like. So what I've done is I've replaced the MOSFET with just a voltage source, which is going to be, you know, the voltage that's present when the switch, the high side switch turns on. And then we've got our two capacitances here, so the gate drain capacitance and the gate source capacitance, and then finally our gate resistor, which is connected to ground, because that's what the driver would do if you've asked the driver to set this low side MOSFET to be off, then what it will do is it will internally connect that to ground. So yeah, that's what we've done there. Now what we're going to do is, first of all, do sort of an AC Thevenin equivalent of this circuit. So we're going to figure out what the voltage source equivalent would be and what the load would be for this circuit. So it's similar to DC Thevenin equivalent analysis. What you would do is, if you had any capacitors when you're doing the DC analysis, you would those would be open circuits, and you would ignore them. So what we do conversely is we remove the resistance, similar to what you would do with the capacitances. So this resistor is now gone. and we have these two capacitors there. So what I can do firstly is try and figure out what the voltage at this point would be. So if I label that VA, and we want to figure out what the voltage there would be, well, it doesn't take very much to see that this is just a capacitive divider, and there is a standard equation that we use for capacitive dividers, which is that the output voltage is simply equal to the top capacitor CGD divided by that plus that, so CGD plus CGS multiplied by your input voltage. So I've written this really poorly, I'm going to move that a bit over there. So if I whack that in, so dV dt, which for the time being, just to simplify things, I'm going to call that V in. Okay, so V out is equal to your input voltage multiplied by your top capacitor divided by the top plus bottom capacitor. Okay, so lastly then, what we need to do is figure out what the equivalent, like what you would do finding out the equivalent resistance of a power supply or something for a DC Thevenin circuit. What we can do here is figure out the equivalent total capacitance that we've got. So to do that, we short all of the supplying voltages. So I'm going to short that. And essentially what we've got here are two capacitors connected in parallel. So the total capacitance then is as I'm sure you know, C total of capacitors in parallel is the same as resistors in series, so we've just got C gate drain plus C gate source. So you just add the two together. And now what we can do is we can construct a equivalent circuit, which would be our input voltage. I'll keep it being on the right hand side because that is sort of how I've been doing it, just so I don't flip things around and make things confusing. We have a capacitor, which we've said is going to be C total. So that's similar to what you would do where you would have like the Thevenin equivalent resistance. You would have some resistance there. It's usually like the internal sort of resistance of a power supply, something like this. And then we reconnect our load, which was RG, so our gate resistance. And what we're actually interested in is the voltage at this point here. So if I put VG there, so that's going to be our gate voltage. Whatever voltage we get here is the voltage that's going to be dropped across the gate of our MOSFET. And if that exceeds the gate threshold voltage of our FET, the FET will turn on. So we need to be able to make sure that VG is ideally much less than the gate threshold voltage of our MOSFET, because as soon as it exceeds that, the MOSFET's going to start turning on. And to be fair, it's even worse if it's you know, just above the gate threshold voltage, because what you're going to do there is you're going to start turning on the MOSFET. It's going to be working in what I think is called the sort of the resistive area of the MOSFET. So it's not fully turned on, and it essentially is a resistor. Okay, so what we've got now is the equivalent circuit that we derived earlier. I've written down what the total capacitance is, because that's going to be important. I've written down what the scaled voltage is, so V in here. That's also important. And then finally I've written the equation for how, just put VT there, for how a capacitor changes its voltage with charge. So basically what we want to be able to do is we want to be able to draw a graph like this that's going to show how the voltage changes as a dV dt event occurs. So it's going to look something like this, okay? And what we're interested in really is this largest magnitude at that point there. So one of the easiest ways of doing this is to essentially calculate the current flowing through this capacitor and dropping its voltage across that resistor. So again, we can calculate the current through a capacitor, which is equal to the input voltage multiplied by, how fast that voltage changes, multiplied by the capacitance. C total we know. dV dt, we know what that will be. The voltage in is essentially just a scaled voltage, scaled by this proportion there. And then finally then, if we want what I've called Vt, which is the voltage when the capacitor is fully charged, then we just simply multiply it by the resistance Rg there. So if I give myself some more room, we know that the final or total voltage that we will see at this point here when this capacitor is fully charged is going to be whatever the current flowing through this capacitance is. So basically the largest current flow through that resistor will give us the highest voltage, multiplied by this resistance. So let's put that it will be the rate of change of the input voltage respect to time, multiplied by this scaling factor here. So I'll call that CGD over CGD plus CGS, multiplied by the capacitance that we've got, which is C total, and that is CGD plus CGS. Finally, I'll put it up here, give myself some more room. We also need to multiply by the resistor, and that gives us a voltage. So you can see quite clearly that those guys cancel out, and all we're left with is this section here. So that's that the final voltage, or the largest voltage that we will see, is the gate resistor multiplied by how fast our voltage is changing, so the rate of change of voltage, multiplied by the gate drain capacitance of the MOSFET. So really, that's the only thing that we really need from the datasheet to figure out what type of voltage spike we're going to induce. But I want to go one more than that. I want to be able to actually plot this type of curve in LTSpice or SMath or MathCAD in something like that. So the way we do that is we've now got what the final voltage or the largest voltage would be seen across this capacitor. And we all know that as a capacitor charges with a constant current source over time, you get an exponential voltage, which is expressed as the final, the largest voltage that you see, the final voltage, multiplied by 1 minus e to the minus t over tau, where tau is the RC time constant, so that would be C total times Rg. And what we can do then is we can substitute this guy into here, and that will give us an equation that we can plot to look at the gate source voltage of a MOSFET. So what I'll do is get rid of this, and I'll write it at the top. So we know that the gate voltage of our MOSFET is going to be equal to Vt, which is our gate resistance, multiplied by the rate of change of voltage, whatever that may be, multiplied by the gate drain capacitance, and then multiplied by, so like this, 1 minus e to the minus t. So that's our variable that we're going to plot so that we can actually see it in time, divided by tau, which I'll just write like this for simplicity's sake, where tau is equal to Rg multiplied by C total, which was CGD plus CGS. Okay, and that's really all there is to it. So what we'll do now is we'll plot this equation in SMath, and we'll model our MOSFET in LTSpice, and we'll just make sure that the two plots concur, and then we can categorically say that this equation is the defining equation for parasitic turn-on, And then we can take a look about what things we can change and what things affect or drive this in order to choose better MOSFETs for our H-bridge applications. So I've actually built a 3-phase inverter using 6 of these MOSFETs, and so this is the ones that I'm going to be using for simulating. I think it will be quite interesting because I should then be able to probe my real-life inverter and see how close our calculations got to the real-life thing. Now, most good MOSFET datasheets will tell you the, well, they refer to it as the input capacitance and output capacitance and reverse transfer capacitance of a MOSFET. Now, what we should know is that these guys, so we've got CISS, that's equal to the gate drain source plus the gate drain capacitance, and CRSS is simply just the gate drain. So once we know the gate drain, we can use this number, subtract it from the gate drain, and that will give us the gate source. But I'm not going to use these numbers here because these are only for these test conditions that we've got written here. I'm not going to be running it at 50 volts at the moment. When I actually do it, it will be close to 50 volts because it's for an e-bike, which is the 48 volt battery. But at the moment I've just got it on a lab power supply set at 25 volts. So what we do is we look at this graph here. So again, a lot of them will have some similar graph like this. And what they've done is they've plotted it at certain, so they've plotted the capacitances at different drain source voltages. This is VDS here. If we choose 25, which is pretty much what I'll be working at, then we've got 100 picofarads for CRSS, which I said was the gate drain. So C gate drain is equal to 100. And then if we continue up, we see that we're pretty much smack on 3000 picofarads for the addition of the gate drain and the gate source. So fairly easily then we can say that the gate source is just 2900 picofarads. So this is all in picofarads. Okay, so we can take those numbers and put that into LT space. So I've already done that here. What I did was I quickly placed down NPN MOSFET. I don't need to select a MOSFET because I'm choosing the characteristics that I want to model, which are the gate drain source and gate source capacitances. I've set up a pulse, which is what you can see up here, so it's quite a fast rise time. It goes to 24 volts in 50 nanoseconds, fairly fast DVDT. And then I've got my gate resistance value here of 5 volts. So we can see that, I can run it again, but we've got a voltage here like what we would expect. It's an exponential rise and then of course an exponential decay, but we're not interested in the decay at the moment. That's probably not correctly modelled. I don't think that's how it would actually happen. But either way, the exponential rise I'm pretty confident with. So we can see it gets to about 240, 0.25 volts. That's not enough to turn the FET on. We could probably look at its drain source. We want its voltage threshold. So let's see if we can find that. So gate source voltage, threshold, gate threshold voltage, minimum 1.2 volts. So as long as we stay away from 1.2 volts, this MOSFET isn't likely to turn on. Absolute maximum is 2.8. So we are, you know, quite far away from that at 0.2 volts. So we've got 1 volt clearance. I'm pretty confident that that's going to be okay. So what I think we should do now is probably plot this the equation that we got in SMath and see how close it is to you know, a circuit simulation. So I shall boot up SMath and I'll see you guys in a minute. Alright guys, so this is a SMath script that I did a little bit earlier on. So SMath, if you haven't heard of it before, is pretty much identical in all intents and purposes to MathCAD, which I'm sure you have used before. It's kind of a non-symbolic sort of computer engine that sort of used, a bit similar to MATLAB, but you have the ability to write anywhere on the screen. You can actually see the equations, how they ought to be written as well, so that's quite nice. It's a bit difficult sometimes to see the MATLAB script. I quite like MATLAB, but I was playing around with SMath, so I just wanted to see it. But what we've got, look, is if I just go through some of the parameters we got. So CGS, obviously that's the gate source capacitance in picofarads, same with the gate drain. I've got RG, which is the gate resistor. My time constant, which is RC, and so we've got also the drain source voltage that will be appearing across the MOSFET, and then we've got the time that we sort of anticipate that rise time might be. So this is the DVDT section. Then we've got a graph plot here, so this basically just says that if it's less than the 50 nanosecond time that I've put in, then I'm going to be doing this equation, which is the equation that we derived. So that's the gate drain capacitance multiplied by DVDT multiplied by a gate resistor, and then there's the exponential function that we've got for the charging voltage. And then there's just a couple of things just out of interest that we can see how large the DVDT is and what the maximum value is that we're going to get. And as you can see, it goes up to 0.25, and that is pretty much in line with what we said here. So if we have a look at that, up to about 0.25. It's not quite there. So there's probably some things that we're not quite modelling, but I would say that that's pretty close. It looks a little bit longer there, but that's, just because of how it is. I think if I was to squeeze it up a bit, it might look a bit similar. But yeah, so I'm pretty happy with that. I'd say that we've successfully modelled that type of equation. Doesn't really matter though. All we can do is we can check what the turn-on voltage is like, the parasitic turn-on voltage is likely to be. By this equation, we can model it if we like, or what we can do is just make sure that the ratio of CGS to CGD is greater than 15. So in this case, we've got GS so we've got CGS over CGD. That gives us 29. So we have a where's it gone? Yes. So one thing with MathCAD is that the placement that you put things actually does matter. So if I stick this up here, it's then above one of these. So it doesn't pick it up, but it doesn't matter. So we have a ratio of 29. That's almost twice as what it needs to be. So that's why this is unlikely to cause us any problems. So what I'll do now is quite interesting, I think, to actually probe on the inverter that I've got and see what type of voltage we're actually getting. Okay guys, so what we've done now, we've looked at the sort of the theory side of it, and what I'd like to do is look a little bit more into sort of the practical aspects of it, so see if we can capture this on a scope. I thought the easiest way of probably doing this is that I've already measured a point on a circuit. I'll explain this circuit in a moment. I've got a screenshot of that which we can look at, and we'll try and do some calculations from there. So this is a three-phase inverter. It's actually for driving brushless DC motors for an e-bike. I won't really go into too much of what we've got here, but if we look inside this point here, we've got kind of a section where we looked at. So this is kind of like a half H bridge driver. So a three-phase BLDC driver. What you could do is basically have 6 FETs like this, and each of those controls a single phase. So for example, if you want current flowing through phase A and phase B in a certain direction to give you a certain rotation, what you would do is you would turn on Q1 and Q4. So you'd have power flowing through here, down this point, through there, or current rather, current flow all the way through there, through the windings of the motor, out and back down through Q4 down to the ground. So what I've got here is the driving circuit. So it looks a little bit different to what we saw, but really there isn't anything different here. So in order to turn on this MOSFET, what you would do is the gate driver IC would provide current here. It's obviously blocked by this diode, so it has to go this way through. This just allows you to have different turn on and turn off gate resistors. So that's quite a good way of having maybe a slower turn on but a faster turn off. In actuality, both of these are 5 ohms for me, but you can change it to different ones should you wish. So that's just a little bit there. But what I've done is I've probed this point here. So the drain of the lower MOSFET, and I've also probed the gate of the low side MOSFET, so that we can see as this Q1 turns on, we'll suddenly get a very 48 volts. It's not actually 48 volts. I'm using a lab power supply, so it's about 27 volts hitting this point here, and through the maths that we just decided before, we figured out before, we should see a small blip in voltage there, and we want to see how accurate our simulations and math were in the real world. So ignore this guy here. This is just a thermal resistor. So this is actually a pretty cool thing for those of you who don't know. It's essentially a resistor, but doesn't conduct any electricity. Rather, it conducts like you can think of it as like thermal energy. So it's quite cool to have connected to the drains of all your FETs, and then connected to a big ground plane, so that you effectively have a very large heat sort of heat dissipator, but you're not coupling any signals into it. So for example, if I was to connect this to a ground plane and this to a ground plane, of course the two drains would be shorted, and that's not a good idea. So yeah, that's a pretty cool thing. So what I've got here is a screenshot. So if I just okay, so what I've got here is a screenshot of the what I was just talking about. So this here is the drain of the low side MOSFET, and as you can see, we're sort of around 0 volts. Then there's a very sharp rise up to, there's some oscillation here. That's most likely due to my grounding. So when I took a picture, I'll probably flash up a picture of the setup here. Maybe I'll put it down here so you guys can see. Yeah, this is most likely due to the ground lead on my probe. So for this measurement, which I'll talk about in a moment, I had the small spring terminal. So I was measuring directly across the gate source of the MOSFET. Here I just clipped a ground lead onto the nearest ground, so there's going to be some inductive pickup. But as you can see, it settles out at what cursor A is, which is 26 volts. And you can see here I've also measured the delta T. So this is how fast it's turning on, approximately. You can see it's not particularly linear, but we can assume it is during that point. And we can see that the time difference there is 19 nanoseconds. So we know right off the bat that the change in voltage is, well, of course, it's from 26 minus 0. So we've got 26 volts there as our dV. dt, the change in time, is what we've got here, so that's 19 nanoseconds, like that, and that is our dV dt. So what do we actually have? Okay, so we said that the CGD is 100 picofarads or thereabout. We know that the gate resistance it's about 5.5, so I measured it with a DMM, that's about 5.5, and of course we know that the dV/dt is this. So if I just change the colors out, make it a little bit more obvious, and I plug those numbers in, we have got 100 picofarads multiplied by 5.5 multiplied by 26 over 19 nanoseconds. And if I get up a calculator, then we can chuck those numbers in. So it's 100 e to the minus 12. I have to press this stupid button to get that to work. So it's 100 picofarads times 5.5 times, then it's 26 over 19, and again the stupid button, so it's e to the minus 9 for nano, and we get 0.75. So that's what they're predicting is the voltage increase on there. So if we have a look, we can see that at around sort of 26 volts, well, maybe we're a little bit down, so we could redo the calculation with perhaps 90. But you know, that's a pretty good estimate, so I'll do it again, but yeah, 0.6, so it's getting even lower. So what we're saying here is that this is about 0.7 volts, it should be. So in actuality, what have we got? So it's 1 volt per division, so there's a volt, so we're already a little bit over that, and there's another division there, yellow lines around about there, which says about half. So it looks like it's actually more like 1.5, so we're about a factor of 2 off. Now that's could be most likely due to this may not be the best method of calculating the time, so it's not too bad. I mean maybe I could have taken it more sort of here. Maybe that's a bit of a, you know, a better way of doing it. I don't know how much more that would add. So looks like we're 1 minor graticule more over, so I could probably redo the numbers again, but as a ballpark figure we can see that, you know, we're well under what the datasheet says is the minimum turn-on voltage. So if we go on to that, gate threshold voltage is 1.2, that's the minimum. Absolute maximum will be 2.8, and we're looking at about 1.5, so maybe, can I zoom? I can't zoom in, so tell you what we'll do. Let's have a look. So we're looking at, so there's 1, so if between there and there is 1 volt, then each of these is 0.2 volts, so we've got 2, 4, 6, 1. So we're about 1.6 maybe. And the data sheet saying, you know, absolute minimum is 1.2, but what we can't see any shoot through. So what probably I ought to do here is potentially lower the RG value. Lowering that is of course going to have a direct impact on VGS. It's about the only thing we can really change. CGD is kind of, you know, that's up to the manufacturers of the MOSFET there. We can't really change that. The dV/dt, there's not a lot I can do about that, really, to be honest. The only sort of thing I've got to play with is RG, so I could probably drop this down to maybe 3 ohms or something. I'd then have to check what my turn-on things. You can see here that this is a turn off curve. It's quite nice and smooth. There's no ringing, which is going to induce any nasty EMI. So I could probably drop it down a bit to 3 ohms, and that would drop this down sufficiently enough that I'm not turning on the FET. But as you can see, there isn't any evidence of shoot through. If there was, you'd see this blue line, doing some horrible stuff. And there would be a lot of, these FETs would be heating up considerably, but I'm not seeing any of that. So, but it is something that maybe I want to change. So what I might do is probably drop this down to 3 ohms, and then maybe make a video on this later showing the differences. But as it's